how are you doing? So for this lecture, we will talk about the first problem from the contest 0, problem wrapper. So this is a nice problem because it has very easy formulation. The task statement is it's very easy, but the problem is quite hard, and the solution, to get the optimal solution, we will need some work to go there. So in the problem, you had two sequences of numbers. And so we have sequence A, sequence B. And there was some story about the rapper who'd like to sell his recordings, and he wants to sell them on the old school vinyls. So for each recording, he had to press a vinyl. And then he is very fashionable, so he wants the vinyls to be covered in glitter. So he contacted two factories, and one factory is pressing the vinyls, and the second factory is covering them in glitter. And for each day, he knows the price he must pay to the factory, and he would like to make. So we have n possible days he can use. So the length of the sequences are n. And he would like to prepare k vinyls. So in order to prepare a vinyl, he needs to decide on some day in factory A. And then he needs to decide on some day in factory B. So for instance, this day. So we can say that, okay, I will make this vinyl. The first vinyl will go to factory A in the third day, and he needs to pay 7. And after that, it goes to factory B and is covered in glitter in day 5. So he can choose the days as he wants, but one restriction is he cannot, the vinyl cannot be covered in glitter before it's produced. So he cannot choose this kind of solution. It's forbidden because first he needs to go to factory A, and then he needs to go to factory B. But he can do this in one day, so this solution is also possible. So in the same day, we are doing in factory A and in factory B. And each factory can make one vinyl each day. So he cannot produce two vinyls here. And he would like to pay as little as possible. So the cost of this should be as small as possible. So for instance, in this solution, if k is equal to 2, we can produce 2 vinyls, paying cost 7 plus 3 plus 7 plus 6. So our cost here in this solution is 7 plus 3 plus 7 plus 6. But this is not the minimal cost. We can do better here. Yeah, so what can we do better, for instance? What we can change to get the lower score? We can, for instance, take this 7 and pair it with 1. But we can do even better. For instance, we can, instead of taking 2 7s, we can take 1 and 3. Okay, and we don't take this one. And also here we can do better. We can take, for instance, 2 and 5 instead of this. So you see that we have some freedom here, and we would like to calculate the minimal cost. So how to to like think about some algorithm here. So I would like to show you the way of thinking about approaching the problems. So usually when the problem is hard, it's not like that you will like instantly find the most optimal solution, like the model solution. Sometimes you need to like go step by step. So first you try to find any solution. Maybe it will be like very slow, but it will like produce correct answer. And then you can think about ways in which you can speed up this solution. So maybe you think about one additional observation which shows you that, okay, this can be speeded up a little bit. Then you think about second observation. So usually like solving the problem is a process. And sometimes the teams are tempted to, oh, I know like n squared solution for this problem, but since n is very big, the solution won't be accepted. It will get time limit. So this idea is bad, and I don't want to go further. And since they don't have another idea, they will just say, okay, we cannot solve this problem. But it's not a very good strategy. Better strategy is like take your first solution and see whether you can think about some additional observations or some additional techniques which will allow you to speed up the algorithm. And sometimes it's very hard to see up front, like when you see the problem statement, what is the optimal algorithm. Sometimes it's better to look at the non-optimal way, non-optimal algorithm, and like play a little with it. So we will for now ignore the constraints on n and k. They are quite big in the problem statements, but first we just ignore them completely, and we just first we can just see what we can do, whether we can propose any algorithm. So what kind of techniques can we try when looking at this kind of problems? So usually if you have like two sequences and you want to like find some solution which takes actually here you take some subsequence from A and some subsequence from B. So we are choosing some elements from A and choosing some elements from B. So do you know a problem which do this kind of trick? Sorry? Okay, so one idea here is we can treat this as a graph, and then we see that this is a bipartite graph, and we can try to find matching. So I will write down this idea. So basically matching in a bipartite graph. And we will go into this idea a little bit further, but can you know any other problems which has like two sequences and you need to find some subsequences in both of them? Yeah, dynamic programming. So this also this also looks promising, especially there's a classical problem of finding the longest common subsequence. So if you have like two sequences and you would like to find the longest, like removing some parts of A, removing some parts of B, you would like the subsequence of A and B to be the same. So for instance, we can take some we can take some inspiration from the longest common subsequence problem. And we will start with this approach. So the approach is as follows. In the longest common subsequence algorithm, we are using dynamic programming. That means that we have to split our problem into some sub-problems, and then we will use an algorithm to solve these sub-problems. So in this standard algorithm, the sub-problem is as follows. So suppose we can we would like to find a solution in some part of our sequences, namely that we can, for instance, so we can only take, let's say, these numbers from some prefix of A and some prefix of B. So let's say that we have here index I, and here we have index j, and we are only interested in numbers in prefix from 1 to I in the first sequence, and in the prefix from 1 to j in the second sequence. And we would like to find a solution to this subproblem. So suppose that we have this subproblem, and we would like to put k vinyls here. So we would like to find k edges. Find k edges with smallest cost. Okay. So what can we say that? So we need to find. So usually, in order to solve this kind of problem, we need to find, for instance, one edge, and then in the rest of the part, we will solve a smaller subproblem. So, for instance, we could say, okay, I can take the edge which is the most to the right. For instance, I can take this edge 1, 3, and then I can solve the subproblem without 1, 3, but with the rest of this part. But the problem is that if we do this in such a way, then this part will no longer be consisting of two prefixes. Okay, because we will delete. Like we will delete 1 and 3, and this will no longer be subsequence. So this is one problem, but we can easily fix this. How can we do this?
Swapping the elements on the B side. If there is a cross, we can swap the axis,
yeah.
So the sum is the same.
Yeah. So basically, the problem we have here is, suppose that in our optimal solution, we have to do a cross. So we have some sequence here, and suppose that we have optimal solution which takes some edges. And suppose that we have a cross in this solution. So that means that we cannot say, for instance, for these two edges, which is right edge and which is left edge, because they cross. But the idea suggested here is that we can actually fairly easily eliminate this cross. Because if something is crossing, we can just say, okay, so instead of taking these edges, we will, 1, 2, 3, 1, 2, okay. So instead of taking these edges, we will take this one and this one. So if we have a cross, we can just swap the edges, and we will get the same cost, because the vertices which are taken are the same. We only change the edges. And we can do this as long as we have some crossings. So that means that there will be an optimal solution in which we do not have any crossings. Okay? So we can use this to produce our dynamic programming. So we can say that, okay, so for this part, I would like to take the edge which is furthest to the right. So I can say, okay, so I can take this edge, 1 and 3, and then I can say the rest of the edges must be to the left of this edge. So then I will have a smaller subproblem with smaller k. So I can write down a formula for dynamic programming. So in our state of dynamic programming, I will have 3 values. I will have value I, value j, which shows me how long these 2 prefixes are, and I also have I will have value k, which says how much of the edges I have to take. So the formula will be as follows. So I have value I, value j, and value k. And I need to consider every possible edge to be the edge which is on the right side. So I will take, and since I will be taking the minimal cost, so I will just take the minimum over all possible edges. So let's say that this edge is on I prime and j prime. So actually these ones will be -1. So I take edge. So let's suppose that we are taking edge. Take edge I prime, g prime. So that means that I prime must be smaller than equal to I, j prime must be smaller than equal to j, and I have also additional constraint, which is? Yeah, I have k, but also when I'm taking this edge. Yes, I have I prime must be less than equal to j prime, because these edges can only go to the right. Okay, and I will take a minimum over what? So first of all, I need to find what is the cost of the edge, and the cost of the edge is a with index I prime plus b with index j prime plus, okay, so I found my edge, plus I need to solve a subproblem which is smaller. So I need to solve the subproblem which consists of 2 prefixes which are to the left of the edge. So the prefix in I must end in, prefix in A must end in I prime -1. In B, it must end in j prime -1. And I have one less edge to consider. Okay, so here I put k -1. Okay, so this is like the main case of the recursion. Of course, we need to also consider base cases. So when our recursion stops. So for instance, our recursion stops when we reach k equal to 0. Because if k is equal to 0, we know we don't need any edges, and we just can return 0. But also we have cases when I or j becomes 0. And then if k is not 0 and I and j is 0, then we know that we have no solution. Because one of our prefixes is empty, but we have to put some edges. So then we can say that the solution is infinity. Because we are trying to minimize the solution, but then we have no solution at all, so we can just say that the solution is infinity. And so usually in this kind of dynamic programming, when you so the solution for the whole problem, of course, is dp of n, and so yeah. So here we have a little bit conflict of names. So let's suppose that the number from the problem is the capital K. So we have to take K, capital K vinyls. So this is the solution for the whole problem. So usually if you get like infinity here, that means there's no solution for the problem. But we can see here that as long as K is smaller or equal to n, we know that we will have solution. So we don't have to worry about this. Okay, so what is the time complexity of this algorithm? Okay, so I heard the answer n to the 5, and okay, and let's see what's why is it so? So in our state we have 3 values, I, j, and k. So I and j can be from 1 to n, and k is from 1 to capital K, but the capital K can be as big as n. So we have n to the power of 3 states. Okay, and how long does it take to calculate the recursive formula? Well, we have to take I prime, and we have to take j prime. Yeah, it says j is less than j, which is true, but we need a j prime here. So in other words, we will need additional n squared for calculating each of the values. So overall, the algorithm is n to the power 5. It's not very fast, but at least we have an algorithm which gives us a correct answer. And especially if you have like individual contests, this kind of algorithms this kind of solutions can be very useful if you want to stress test your best solution. So for instance, if in your best solution you get wrong answer after sending to the judge, you can like write this very easy but very slow but the solution which gives you the correct answer, and then you can just randomly generate some tests and finds whether these 2 solutions will give you the same answer or different answer. And if they give you the different answer, then you have the counterexample. You have a test on which you differ, so we can look at this test and see why your best solution gives bad answer to this test. So this is the quite powerful technique to do the fast debugging. Of course, if you're like working in a team, then you must give the priorities to different things. For instance, if you want to do stress testing, you need a computer. Maybe perhaps your teammates have some code to write. So you have to like choose whether you'd like to use this technique. But for instance, if you like working on one problem, like in your team, then this is like a really fast way to do the debugging. If you have like no idea why your algorithm doesn't work. Okay, but oh sorry. I would like to know how much time do I have? Yeah, yeah. This one is. It's counting backwards. Okay. So okay. Thank you. So we have like this this idea of a solution, but we can speed it up quite easily using this dynamic approach. So one thing which is very costly here is this loop. Okay, and any ideas how we can improve it?
We can choose like between discarding the element in the first sequence or discarding the element in the second sequence. Take both as an edge and decrease both.
Yes, yes. Then that's the very good idea. So instead of like considering every possible edge in this subproblem as the rightmost edge, we can just say, okay, we can take only ij as an edge. Okay, and every time we have a subproblem ijk, we have only two possibilities. Either we take this edge ij, or we don't. Well, actually, if we don't, we have another two possibilities. Because if we don't take the edge ij, then we know that for sure we won't take either I or j. So we can write down a second formula. So dp of ij and k is equal to, so either we take the edge ij, so we will have several cases, and we would like to take the minimal of all these cases. So either we take ai plus bj, and then we need to consider a smaller subproblem. So the smaller subproblem is just dp I minus 1, j minus 1, and k minus 1. Okay? Or we don't take this ij edge. And if we don't take this edge, then we know that at least one of these vertices will never be taken. So we can shorten one of the prefixes. So we can say, if we make the first prefix shorter, then we have a subproblem in which first prefix shorter by 1, second prefix stays the same, and the value k also stays the same because we didn't use any edge. We didn't take any edge. And the symmetrical case is when the first prefix stays the same, but the second prefix get a little bit shorter, and we are not using any edge. Okay? So here we still have n to the power of 3 states in our dynamic programming, but for each state we are calculating the transition in constant time. So we have like only 3 transitions. So here the overall time complexity was n to the power of 5, but for this solution our complexity is n to the power of 3. Okay, so we get a quite improvement starting from n to the 5 going to n to the 3. But for this problem we will get some more improvement. And actually I think that this dynamic programming approach for this problem won't get us much further. So, but we still had some ideas about this problem, namely that the suggestion was that maybe we can use a matching in bipartite graph. So sometimes you need to also think about different approaches. So what is the second approach is about? So basically you can think about your problem as a graph. So you have a graph, you have some vertices. So each each of the number in sequence A and sequence B will be a vertex in a graph. So maybe I will, yeah, I think I will just erase for now everything which is not the sequence. Okay, so we will start from the scratch. So we have vertices in the graph, n vertices at the top and n vertices at the bottom. And we can if we have a graph, we also need to have edges. So in this graph, the graph structure will be very easy. So for each vertex at the top, we will have edge to the vertex to the corresponding vertex at the bottom, and also to all the vertices which are to the right of this vertex. And we are doing this for every vertex in set A. Okay, so for instance, for this vertex, we will have 2 edges. In the first vertex, we will have like edges to everything else. So this graph is very simple. And on this graph, we would like to find a matching which has k edges. A matching in a graph is just a subset of edges in such a way that these edges do not touch themselves. So they are just they are disconnected. So for every vertex, we can have at most one edge which is adjacent to this vertex. So basically, in our problem, we need to find a matching in this graph. For instance, we can take this edge into the matching, this edge. So we need a matching of size k, and additional restriction is we would like this matching to be this matching will also have a cost, and the cost of the matching will be just the cost, the sum of the costs of the vertices in this matching. Okay, so we can try to think about like standard algorithms which calculates this kind of matching, and see which of the algorithms can we use here. Mm-hmm.
Maybe you can use a flow on the graph.
Mm-hmm. Yeah, we can for instance use flows on graphs. So we can build this graph, and usually if you, yeah, I think I will erase the dynamic programming. So usually if you think about this, you can use some algorithms which like directly construct some matching, but you can also use some algorithms which construct flows. And for this algorithms, you also have additional thing, because you can use algorithms which construct flows which has minimal cost. So this is an algorithm for constructing a flow with minimal cost, and you can construct a graph which so we take this graph from our problem. In each edge, for each vertex, you will have edges, and also we will have additional vertex at the top and additional vertex at the bottom, and we will connect every vertex from the top, from the A to the top, and every vertex from B to the bottom vertex. Okay, and we would like to use the min cost max flow algorithm. So basically, this algorithm allows us to find the flow from the top to the bottom. So the flow is, in our simple example, it will be just paths which goes from the top, goes here, and ends at the bottom. And we will say that each edge has capacity 1. So each edge has capacity 1. That means that only one path can go through each edge. So in fact, these paths here, which are found by the algorithm, will be disjoint. Okay? And the MaxFlow algorithm finds us the maximal number of disjoint paths we can push from, let's say that this is vertex S, this is vertex T, which push from vertex S to vertex T. But we don't want a maximal number of such paths, because what is the maximal number path in our problem? It's always n, because we can just push the paths like we can just push simple paths, like from the top vertex to the corresponding bottom one. So we need to find a way to constrain the number of paths.
Adding additional vectors.
Sorry?
Adding additional vectors pointing to S with capacity K.
Yes, we can add additional. So if we, the idea is we can add additional edge with capacity K. So this will be like special edge, which has capacity K. That means that through this edge only K paths can go. So this will restrict our solution to have only K paths. Okay? So MaxFlow algorithm will find us K paths. But we are actually interested also in K paths will give us the smallest cost. But for this we can use min cost MaxFlow algorithm. So for each edge, also we need to describe what will be the cost of this edge and how we can do this. Okay, so for each of the edges, we put what? So for edges which goes from, so let's say that these are edges from set B, these are edges from set A. So for each edge which goes from set B to the sink, so to the last vertex, we will put the cost equal to Bi. So the first edge has cost B1, the second has cost B2, the third one has cost B3. And for each edges which goes from S, so from the source to the A, we will put cost equal to AI. And these edges here we will have cost 0, and this one also has cost 0. So if we run the min cost MaxFlow on this algorithm, we will get some set of paths. We will get exactly K paths, because we know that our graph is very simple. So we can even push here n paths. But we are constrained here by K, so we know that we will find K paths. So here we are okay. And we know we will find such a paths that the cost of these paths will be as minimal as possible. So basically, if we look at all the paths, we can say that if the path goes through this vertex and through this vertex, so the cost of this path will be AI plus Bj. So this will be the cost of the edge which we can take. And this is true for all paths. So having these paths, we can construct our solution. And since we know that min cost max flow will give us this flow of minimal cost, so we know that this solution will have the minimum possible cost. Okay? So we can use this. Unfortunately, so these are, we have like good things here and bad things. Well, good thing is this, that min cost max flow is a standard algorithm. It's not like it's not an easy algorithm to to come up, but usually like for harder problems with graphs, you can find some solutions which requires you to use this algorithm. And because like it's a kind of standard one, I didn't want like to present it here in the lecture in full, because you can find like many materials or tutorials in the internet about this algorithm. But the thing is that, and usually on the contest, you will, if you want to use this algorithm, you will have it pre-written. So you will have it in your library of pre-written algorithms you can use. And then it's just a matter of typing out this algorithm. And so it's like important how to use it in the problem. So this is like a good thing, I think. But the bad thing is that for this problem, the min cost max flow has not a very good time complexity, because like even the fastest ones, even if you like write the algorithm which has like cost n to the power of 3 when n is number of vertices, and it still is a like really good implementation if you have this kind of algorithm, then we see that still the number of vertices in this graph is n. So this will give you the algorithm of time complexity no better than n to the power of 3. Maybe even n to the power of 4 or 5, depending on what kind of min cost max flow algorithm you have in the library. But it's another solution to this problem, and actually this solution is quite nice, that it will allow us to get better complexity than n to the power of 3. And to get this better complexity, we will need to remember, or we will need to learn how actually what is the principle on which this algorithm works. So how it works a little bit in detail. So I think I will erase this one. So basically, you can, for finding the, so here we are using this max flow algorithm to find the maximum matching. But if we want to find the maximum matching, actually there are some easier algorithms for doing that. We don't need to use flow, but both these easier algorithms and flow algorithms, they operate on the same principle. And one of the principles of these algorithms is that we can take, if we would like to find a matching which has k edges, we can take some smaller matching which has fewer edges, and we can somehow expand this solution to get a bigger solution. And this expansion is done through a notion of augmenting paths. And we'll recall what does it mean. So suppose that we have some graph. So we have some edges. So first let's forget about that our graph has some special properties. Let's suppose that we have any graph. And suppose that we have already constructed some matching. So maybe we have like let's write down some more edges. So so maybe we have some edge in the matching. So for instance, this one, we can think of this one, and maybe this one. Okay, so we have a matching which with size 3. Is it a maximal matching? So the question is, can we find a matching which has more edges in this particular graph? And the answer is yes. We can find this bigger matching, and we can find it. So one way to find it, you like erase everything and try from scratch, and maybe you find something bigger. But also we can try to expand this one. And in trying to expand this one, we can think, okay, so we can take some easy cases. For instance, we can say, okay, so this vertex is not matched, but actually from this vertex you have an edge to another vertex which is also not matched. Okay, so we have like this edge. You can just add it to your matching, and you have just increased your matching by 1. But so this is like the easy case. So now you have this graph, and you are still wondering whether I can increase this matching or not. Because like you see, you have some vertices which are not matched. Of course, like this guy is not matched, but there's no edge from this vertex, so you definitely cannot like extend the matching using this vertex. But you have some additional vertices which have some edges which goes through them.
I can go from a vertex to the vertex that I firstly connect and see if it has another edge connected to it that can be another match. So if I can do that, I can return and check if I have another edge connected.
Okay.
And check if I can connect it with it.
Exactly. So that's the idea we would like to use. So suppose that I start from this vertex here. So the only edge from this vertex is this one, but unfortunately this vertex here up is already matched. So I cannot just add this edge to the matching, because this will be like, I cannot have two edges which goes to the same vertex. So, but I say, okay, so let's see what happens with this matched edge. So let's see what happens with here. Okay, and I will go down here. So I see that from this vertex, I still have some free edge. So I will go through this edge. And I see, okay, so this vertex is also matched, but I can traverse through this matched edge, and maybe I will finally find some vertex which was not matched. Okay, so what I'm constructing here, I'm constructing a path which has, if I draw this green path, so this will look like this. So if I draw this green path, this will look like, it will consist of the vertex which is not in a matching. It will consist of another two vertices which are matched with an edge, another edge which is not in the matching, another edge which is in the matching, and finally edge which is not in the matching. So I have this path which has every other edge is not in the matching, and the subsequent edges are in the matching, and these edges are free. So basically what I can do, I can take this And instead, I can construct this matching. Okay, so I can, on this path, I'm just flipping each edge. The edges which were in the matching are no longer in the matching, and the other edges are in the matching. And we have 2 edges, and now we have 3 edges. So for this patch, I just increased the number of edges which are in the matching. Okay, so that means that I can do this, and there's a theorem which says that if you have a matching which is not maximal possible, then you actually can find such a path on which you can extend this matching. And I think it's quite nice to see the proof. Why is it true? So let's suppose that you have a graph. Okay? You have a graph, and in this graph you have found some matching. Let's draw this matching in red. And you say that, okay, this matching is not maximal because I can, well, and this graph is, but I can say that this is not maximal because there's some another graph. So maybe let's make an example here. Oh, okay, because there's some another graph in which I can. Well, this is the same graph, but I can find a better matching in this graph. So, for instance, this is like the better matching. So maybe this example is not the best one I can think of, yeah, because this edge is like really trivial to add. So maybe let's write something like, so we don't have this edge, but we have, for instance, this edge, okay? And here I know that there's some matching which is better. So for instance, I can take this guy and this guy. Okay, so here I know that I have some matching M, which is not maximal, and here I have some matching M, let's call it opt. Like optimal matching, the maximal one. And what I can do, I can just take both of these matchings and put them on the same graph. Okay? And the way we will do this, we will say that this will gives us something strange, but let's say that we would like to take this as follows. If some edge is only in one matching, then we will color it. Then we will call it like green. And if some edge is in no matchings, then we won't color it. Okay, and now it's we can do it this way, or okay, let me think what we would like to do here. Okay, so now let's say that we have this this bigger. Let's take all of these colors and put them in the same graph. So then we will have some edges which are blue, and we will have some edges which are red, and possibly we will have some edges which are red and blue. Okay, but like for every vertex in this graph, so we can like make a picture. We can like make a picture for this graph. So for every edge, like so maybe we won't be like calling the vertices. We will color edges. So this edge is red, and this edge is red, and this is also blue, and this is blue, and this is blue. Okay. So if you think about these colorings, the red and blue colorings, because red edges and blue edges were matchings, that means that for every edge, for every vertex, you can have like at most one red edge and at most one blue edge. So that means that if we only look at the colorings, that means that for every vertex, you have at most two things which comes out from this vertex. So the degree of each vertex is at most 2. So if you have a graph in which you have each vertex has at most 2, then this graph is very simple, because it can has only 2 structures. It can has only cycles or paths. So for instance, here in our graph, we have a path which is like blue, red, blue. Okay. And we have this like little cycle, which is will be not necessarily like. So this is like this trivial cycle in which have an edge which goes blue and then it go back in red. So we can have also this kind of cycles. But for other graphs, we can have like cycles. Maybe we can have like bigger cycle. So, and in this cycle, every edge, like every other edge must be red, and the rest of the edges must be blue. Yeah, because we, like for every vertex, we cannot have 2 red edges which goes into the same vertex, because then the red edges wouldn't be a matching. So this means that this cycle must have like red, blue, red, blue, red, blue. And that, for instance, that means that the cycle must be of even length. Yes? Because so the number of edges must be even. That means that also means that there's the same number of red edges as the same numbers of blue edges in this cycle. And this is true for every cycle. In every cycle, we have the same number of blue and the same number of reds. And for paths, the paths can be of different lengths. The path can be of even length. And for even length, well, still the paths must be colored with red and blue. So for even paths, the number of reds and the number of blues must be the same. So for these paths of even length, for cycles, and for these small cycles, we know that the number of blue edges and red edges are the same. So the only paths in which we can do otherwise are these paths of odd length. Okay? So we have two kinds of these paths. We have paths which starts with blue edge, and we have paths which starts with red edge. And for every path in which the blue edge is the first one, we have one more blue edge for this path. And for every path in which we are starting with the red edge, we have one more red path. Okay? But we were told that the number of red edges is smaller than number of blue edges, because this matching was not optimal. Okay, so if number of red edges is smaller than blue edges, so what we can say about the number of the paths? So we know that the number of red edges is smaller than number of blue edges, and we say that for every cycle and for every path of even length, these numbers of blue and reds are the same. So the only structures in which these numbers differ are these paths and these paths. So we know that there must be at least one path of this kind. Okay, but actually this path is an augmenting path you would like to use. Because now if we take this path in a graph and we apply it to this red graph, so if we apply it in such a way that we take every red edge from this path and we just remove it from the matching, and we take every blue path from here and we insert it in this matching, we will get matching which has one edge, which is one edge bigger. Okay, so this theorem says that if this matching is not maximal, then there is some path which we can use to make this matching one edge bigger. So we can use this theorem as long as we need. So if we end up with a situation with a graph which don't have such a path, then we can know for sure that we have maximum matching. Okay? So now the question is, how can we find such a path? And there's a standard algorithm for this, which works in bipartite graphs. Basically, you need to start in any vertex which is not matched, and you just have to go using any algorithm for traversing graphs you'd like, for instance, DFS or BFS, visiting these edges. So from each vertex at the bottom, you just use every possible edge which is free, and from vertices at the top, you must use edge which is in the matching. And going through this graph, you can just make vertex. You can visit these vertices in such a way that if you visited the vertex once, you don't have to visit it more than once. So in general graphs, this won't work, but in bipartite graph it will work. And if during this search you will find this kind of path, then you can just use it. And if you don't find it, then you know that the matching is maximum. Okay, that means if we see this algorithm, that means that we are starting from the matching, and we will, using these paths, we will add, in every phase we will add one more edge to the matching. So that means that if we use k phases of this algorithm, we are sure that we have k edges in the matching. Okay, so back to our question. In our question, the problem was how to find a matching which will have minimal cost. So the cost of matched vertices will be as small as possible. So we can also use the same algorithm for this, because we can see, so basically we will use this algorithm of finding the paths, but now we will be finding a path which has smallest cost. And the cost of the path will be just cost of vertices we are adding to the path. So in each phase, we will find from each vertex which is not matched, we will find a path to some other vertex which is not matched, and the cost of this path is just, let's say here we have like B1, and here we have like 1, 2, 3, 4, 5, A6. So why can we say that this is the cost of the path? So if we have some matching which has some value, so basically the value of the matching is just a sum of costs which were taken in the top and sum of costs which were taken in the bottom. And every time we change the matching using the path, we will be adding some vertex B which was not previously matched. So we need to add this B1 to the cost of the new matching. And also this vertex was not previously matched, so we also need to add A6 to the cost of the matching. But why is that we only need to do this to get the correct cost of the new matching?
Because every other vertex is still matched.
Yes, exactly. Every other vertex in the graph which was previously matched will be also matched. So like in this picture, so these vertices here, this one, this one, this one, and this one were previously matched, so they have some cost, but in this new matching, they will also be matched. They will be matched by different edges. So like for this node, instead of this edge, we'll use this edge, but they will still be matched. So the cost for these vertices does not change. So we only need to add these two vertices to the cost. Okay, and the question is, so why can we do this in phases? So why can we like applying the paths with smaller costs? Because it's obvious that if we start from some matching and we would like to increase it using some augmenting path, it's best to use a path in which B1 and A6, so namely this new vertices which are adding to this matching have the smaller cost, because otherwise we could just use another augmenting path to get the better cost. But the thing is, why can we start like from empty matching and add every time adding augmenting path with the smallest cost? So why this procedure will give us the matching with minimal cost? So, somebody wanted to.
Maybe
Uh-huh.
like contradiction. Like if we have another matching with more cost, we can like kind of swap one match with another that have lower cost.
Yeah. So basically, the argument we can provide here, I think, two arguments. One argument is we can show a similar proof here, which uses these ideas. So in this proof, we can show that if we have some matching M which has some smaller cost, then we can see what kind of structures we will have for this matching. So once again, if we consider cycles, So we know that if we have like a blue matching on the cycle and red matching on the cycle, both of these matchings match all the vertices on the cycle. So like the cost of red matching here and the cost of blue matching here is the same. So for cycles, we don't have to worry about them. The one problem is with paths of odd, even length, because now the costs of these paths are not necessarily the same. So for red path, these are these vertices, and for blue path, these vertices. So now possibly we have like a additional path which will gives us smaller cost. But the thing is that if we have such a path, that means that we could use this before. So as long as we always using the paths of smaller sizes, we know that this path won't. We won't have a path of this kind. And we can like use the similar algorithm to show that that using the paths of smaller cost is good here. Another argument is if we like we show this this algorithm here, but if you know how the min-cost max-flow algorithm works, it basically works in a very similar way. I mean, it works in phases, in each phase you will find a path of minimal cost, and will increase this flow along the path of minimal cost. So basically, what the min-cost max-flow does on this graph, it's essentially the same what we are doing on this graph. And we know that min-cost max-flow algorithm is correct. So we know that in min-cost max-flow we can increase the flow using paths of smaller sizes, like of the smallest costs. So because this algorithm is okay, so we know that our algorithm is also okay. So this is like the second proof why this is okay. So in our algorithm, we need to do as follows. We will have n phases. So yeah, so let's look at what is the time complexity of this algorithm. So we have n phases. And in each phase, we need to find an augmenting path which has smaller cost of the first vertex plus the last vertex of the path. Okay? What is the time complexity of finding such a path? Linear in terms of in terms of number of vertices or number of graphs of edges? Because the problem is that if we would like to find a path, we possibly need to like traverse the whole graph. Okay, and the problem is that this graph has the number of edges is quadratic in terms of number of vertices. Because like, for instance, for this vertex, in our graph, in graph from the problem, this vertex is connected like with everyone else. This vertex is connected with n-1 vertices, this is connected with n-2, so the graph has n square edges. So if finding one path takes us time n square, then the whole algorithm will take n to the power of 3. So still it's not better than the dynamic programming we had previously. So previously we had this easy algorithm with dynamic programming, and then we do a lot of work which ended with algorithm which has no better complexity. Then we can think, okay, so why doing all this work? So the answer is that we are not finished here, and the thing is that this algorithm we presented here works for any graph, any bipartite graph. So it doesn't depend on which edges are in this graph and which edges are not in this graph. But our graph has very special structure, a very nice structure, and we should use this structure to get if we would like to get algorithm which is faster. Okay, so let's see. So let's see how the structure of the graph will help us. So remember that in our graph, every vertex from the top is connected to every vertex from the bottom, which lies to the right. Okay? So let's suppose that we would like to find an augmenting path starting from this vertex. Well, we can start finding augmenting paths from vertices in B, but we can also start with A. It doesn't really matter. So let's suppose that we have some matching. So perhaps something like this, something like this. Okay, so let's suppose that we have matching of size 2, and we'd like to find a matching of size 3. So what can we do with this vertex? Well, this is kind of easy because we have some unmatched edges from this vertex, so we can take this edge, for instance. And this will be correct, perfect match. And in fact, our graph has many edges. So at least in first phases, we will most of the phases will end up. Okay, I can take one edge because it's kind of easy. So let's and actually I don't have to care about that these guys are crossing each other, in this dynamic programming algorithm, because I can say, okay, it doesn't really matter whether it cross or not. If I'm interested in some matching which does not cross, so I can take any matching, and I can by uncrossing these edges I can create a matching which does not cross. So this is not a problem here. But we can have a little bit more complicated things. So suppose that we already have some matching. Let's say that it goes here. So we will go here. We will go. Okay, let's say that we have this kind of matching, and let's say that we run our algorithm to find the augmenting path, and this algorithm maybe starts from this vertex. It goes here. Well, this is already taken, so we will go here. From this vertex, maybe we will go here. This is taken, so we will go here, and from this vertex we will go here. So maybe our algorithm will find this kind of augmenting path. Okay? So what can we say about this path in our special graph? So basically this path increases the matching by taking this vertex and this vertex. And it does that using like this long path. So, can we do something simpler?
Yes, we can take the edge directly.
Yeah, we can take the direct edge. Instead of taking this path, we can just take this edge. Okay? And why is it so? Well, the thing is that this green vertex here is to the right of this vertex here. So if we happen to find two vertices with a pair of vertex, like a vertex from A and a vertex from B, which has the smallest total sum, and vertex from A is to the left of vertex of B, then we can just pair them up. Because there will be an edge from A to B, so we can just take this and say that this is our augmenting path. So we can think about this algorithm. So let's say that we have some vertex. So let's say that we augmented this already, and we have among these three vertices, which are free, this vertex will be the minimal value. So this is mean value in A. So if we take this one, and this one, this is the minimum. And let's say that in B, we also inspected these vertices, and this is mean value in B. So if we have something like this, then we can say, the minimal sum will be mean value in A and mean value in B. And since I can connect them with an edge, I can just add this edge as an augmenting path. And I will get correct solution which has one more edge. Okay? So this is like an easy case. But we can have some case which is a little bit more complicated. So suppose that we have a case here that this is mean value in B. So what can we do now? So now I cannot like just add them together in a simple way, because there's no edge between A and B. So the thing is, I must answer the question whether there's some augmenting path between A and B. Okay. So, and in order to do this, I can like run the algorithm, but I can also think a little bit more careful what is going on with our graph. And yeah, so let's say that we don't have because I would like to know which edges are already in our graph and which are not. So let's suppose that we don't have these green edges. We have red edges and we have blue edge. Okay, so this is the matching in our graph. And actually we can make it a little bit easier for us. So let's say that these edges are not crossing. It will be, so this is also correct matching. Okay, so the question is there an augmenting path from A to B, from this vertex to this vertex? Okay, who thinks that there is no such path? Raise your hand. And who thinks that there is such a path? Okay. And who didn't vote? Well, come on. Okay, so actually there is such a path. So for instance, we can go, remember, when going like with edges, we can only go to the right. So from this vertex, we can take, for instance, we can go here. But now, when we are using the edges from the matching, so now we have to use a red edge. So we can go, actually, we can go back using this edge. And now from this edge, we can go, for instance, here. And now we can go back. Okay? And from this edge, we can go here. Okay? So we see that there is an augmenting path from this vertex to this one. And we can just, and since this was the minimal value in A, and this was the minimal value of B, then we can connect them together. Because this will be the minimal augmenting path. So sometimes we will have these paths, sometimes we won't have these paths. So let's say that our graph is we have two additional vertices in it. Yeah, maybe I will erase it and create a new example. So let's say that we have 4 vertices, and our matching was something like this. So these guys were in the matching. And let's say that this vertex is minimum in A, and this vertex is minimum in B. So question is, do we have an augmenting path which connects A to B? Okay, some people shake their heads, but there is no such a path. And actually, yeah, there's no such path. And why there's no such path? Well, if we want to use normal edges, then we need to go to the right. We can only go back using these red edges from the matching. But the problem is that here we cannot cross this border. Yeah, because there's no red edge which travels from the right part of the graph to the left part of the graph. So no matter what we do, well, we can, for instance, we could like take this edge, then we can go a little bit back, then we can like take this edge, but we really cannot go to the left part because there's no red edge which goes from the right part to the left part. So in this case, we cannot add any augmenting path which starts on the right side and go to the left side. So now, well, we have to do something more clever. So let's recap what we found so far. Let's see what we have found so far. So we have found that we have two kinds of augmenting paths in our graph. We have I would say easy paths. So an easy path is a path which connects a vertex from the top with vertex on the bottom, and it goes to the right. So suppose we found like a vertex with small value at the top and small value at the bottom, and the bottom one is to the right, we can just connect them And we know that this is augmenting path in our graph. We don't need to like run any algorithm for this, any special algorithm. But we also have these vertices which are like we can inspect the pairs of vertices in which the bottom vertex is to the left of the top vertex. So we would like to create some augmenting path here, but we don't use it directly. We only can use this path if we have some red edges, so the edges from the matching to support it. So, for instance, if we have like this edge and maybe this edge, so in this case we can add this, but there are some cases where we cannot. And the question is how this red edges must be like. What properties do they need to have in order that we have this augmenting path?
Like every like neighbor edge can be like one vertex be right. Like the difference between the lower part of the sequence of one red edge and the upper part of the sequence. Some other edge can be like more than one, like they must be like intersected in some way.
Yes, so the idea is that these red edges must somehow intersect. I mean, not in the way that they cross, but it must be possible to go from one red edge to another red edge, like going only to the right. So if we like draw these edges like this one goes from here to here, and this goes from here to here. So if we just make the if we just draw the ranges on which these edges are, then these ranges must overlap. Okay? So if we have some picture. I'm drawing a lot of graphs today. So if we have some matching, for instance, this goes here, this goes here, maybe this goes here. Yeah, maybe we will make it even bigger. This is here, this. Okay, so as long as these edges like overlap, then we can make an augmenting path. So for instance, we can take this graph and we can partition this graph into blocks in such a way that in the block these red edges will just overlap each other. So for instance, let's say we are starting from the right. So we start some block and we see that we have a red edge. And this red edge goes from this vertex up to here. So we know that in this part, we have a red edge which goes to the left. So in this part, we will have a support to make an augmenting path. But also, this edge intersects it covers this bottom edge. So actually, we can even go further. We can extend this even further. And that means that we can end our block here. And this means that from any vertex from the top, we can connect it to any vertex from the bottom using an augmenting path. Okay, is it clear? Because we can see that like from any of these guys, we can go to the last one. From the last one, you can go here. From here, we can go here. From here, we can go to the first one. And from the first one, we can go anywhere. So that's the idea. Like from any vertex, we can go to the last one. From the last one, we have enough red edges to go to the first one. And from the first one, you can go to anywhere. Okay? So what will be the next block in our graph?
Right, to the left.
There, in the next block, we will have only one edge. The next block, well, this block is kind of special because it doesn't have any additional vertices which we can match. The next block will be also kind of special. This is a block in which we don't have any red edges. So, if we have two vertices in which like one above another and both are not matched, then this is the best we can do. And what about the next block?
Because the beginning of the left, that's right.
So how many vertices will be in the next block? 4. And that means that, again, we can take any blue vertex. We can, from any blue vertex, we can go to the last one. Here we can traverse red edges, and from this one we can go here. And the last block will just consist of just one vertex. Okay? So, if we have this partition into blocks, then we know something like this. If we have this partition, now in order to find the best augmenting path, we have to consider two possibilities. Either the path is a trivial path, so either it connects some vertex from the top with some vertex to the right. Okay? So among all possible such paths, we would like to know what is the path of minimal cost. Okay, and this will be case 1. Okay? And what will be the case 2? In case 2, we would like to consider all the, I would say, non-trivial paths. So the paths which goes from the right in the top to the left in the bottom. So which paths will be non-trivial? Which paths we can take?
The ones in the blocks.
Sorry?
The ones in the blocks.
The ones in the blocks. So for sure, the path cannot, so this non-trivial path cannot connect vertices which are in different blocks. So we need to only consider paths which are inside one block. Okay? And so we need to treat these blocks separately. So what can we do for a single block?
Find the minimum in both sides and add them.
Yeah. So because in a block, like if you have a single block, you know that you can connect everything from the top to everything from the bottom. So actually for a block, we need to find any, like the vertex which is minimal at the top. So we just find minimum at the top, we just find minimum at the bottom, and we know that we can join them together. So for the block, we do as follows. We find the minimal at the top, minimal at the bottom, and this will be the best path we can use in this block. So now we are doing this for every possible block, finding this best path, and we take the path which is minimal. Okay? Across all these blocks. So case 2 is quite simple. Just iterate over blocks and in each block find the minimal path. Case 2 is in some sense easier because we are not constrained to blocks. We can take like any vertex from the top and any vertex from the bottom. So in this sense, this case is easier, but it's also a little bit more complicated because we need to take care about the fact that the vertex at the top must be to the left of the vertex at the bottom. Okay? And for paths in the blocks, we don't have this assumption. So actually, the case is like when we are finding non-trivial paths in the block, maybe we will find here a path which is actually trivial. So sometimes it will be the best, even inside the block, to connect two vertices in such a way that they can be connected with an edge. So maybe, like in this block, maybe this is like minimum A, and this is minimum B. So we know that actually this path here, like this is a trivial path. But since this is the best path in this block, so we know that no non-trivial path in this block is better. So we can just also use this one. Okay? All right. So we are here. So now we need to So now we know some additional things. We have this notion of trivial paths, non-trivial paths, and we would like to come up with some algorithm. So what can we do? So our algorithm still will be working in phases, and in each phase we will find the best path. But now we won't be like finding these paths using the standard algorithm. We will use our additional knowledge. So actually we will be finding this minimal vertices at the top and minimal vertices at the bottom, and we will just mark them that okay, they're connected. So what can we do in one phase? So what are we doing in the phase? So first, let's consider case 1. Okay. So we need to find a vertex. So we need to find such a path, such a pair, that we have some vertex A here, vertex B here. A is to the left of B, and their sum is minimal. So how can we do this fast? Okay. Well, one idea would be we can just like try every pair, try every possibility. So, but this wouldn't be very fast because in trying every possibility, we just try n squared values. Okay. So another thing would be okay. So let's fix some vertex A. So let's try every possible of vertex A. Okay. And yeah, and we know that we need to only try all the vertices which are like to the right of them. So we need to find the minimum here. So maybe if here we have like more vertices. So we only need to find the minimum on this section, and this section is just a suffix of our array. Okay. And for other vertex, for instance, if we would like to find the minimal using the next vertex A, we need to find the minimum in this suffix. So how to do that fast?
Second.
And I iterate from right to left and with a variable we generate the current.
Yeah, exactly. So I think I also heard some about tree. So for this one, also we can use like a segment tree, which gives us like the which allows us to make queries over ranges. But this idea here is much simpler. So basically, we will be keeping the running minimum of the range. So we will start. So we will be going with vertices A from right to left. So suppose that we are here, or okay, maybe we can like, yeah. Suppose that we are here and we already calculated the minimum for this vertex A. So we know that, so this is like green minimum. So we know that if we want to calculate the minimum for the next vertex, so the blue minimum, so let's say that this is minimum with vertices B. So if we know that if we want to calculate the minimum for the blue vertex, this is just taking the minimum from this guy. So this is like, let's say that this is BI. And the minimum we have found so far. So the green minimum. Okay? So if we go from right to left, we can find a minimum for the next A vertex in constant time. Okay? So for each vertex for each top vertex, we will find the minimal vertex at the bottom in constant time. So overall, this whole phase will work in linear time. And this is case 1. So we solve case 1. And okay. And now we would like to solve case 2. So here we found the best trivial augmenting path, and now we'd like to find the best non-trivial augmenting path. So suppose that so for this we have to do 2 parts. In the first part, we need to partition our graph into blocks. So let's say that we have this partition. We have these blocks in the graph. So what should we do to calculate case 2?
Find like the smallest vertex that I haven't used yet, and then like try checking if it's also the smallest one in the second sequence is to my right, or it's like to my left, but on the same block.
Yeah. So basically, we can iterate over each block, and in each block we don't really care about what is the positioning of these 2 vertices. In each block, we need to find the minimal at the top and minimal at the bottom, which were not used before.
Can it be the case that, for example, in that second block, I can pick one vertex in the upper part and connect it with some vertex in the last block from the lower part?
Well, I can pick any vertex in this block and any vertex in this block, but I cannot pick any vertex in the next block.
Isn't it valid to connect, for example, the third vertex with the last one, even if they are not in the same block, because the last one in the lower sequence is to the right of the third one in the first sequence?
Okay, so then let's say that we haven't connected. So which one? To which one?
For example, that one with
That one?
I don't know, with the last
with the last
The
one?
last one in the end of the sequence. Like,
In this one?
yeah, isn't that?
Yeah, it's not. Well, if we want to connect this one to this one, this is trivial. This is case 1. Okay? So we already solved this. Okay? We already solved all the cases in which we are connecting this guy to some guy on the right. Okay? And we can do this without any blocks. And we already solved this here. Now we only solving the problem for the non-trivial paths. So the paths which are inside one block and which goes from right to left. But actually for these paths we really don't care whether they go like from right to left or from left to right until they are in the same block. For the same block we just take every guy in the top and every guy at the bottom and we just take the minimum. Okay? But now there's a question how to partition these guys into blocks. How to partition this graph into blocks.
We can take like each edge as a segment, as a range, and then like try to iterate, taking into account like if I leave some edge, there's like a blank space and that's the end of a block. Otherwise, I continue like merging one range with the other.
Yeah. So basically, we can like go from left to right, and we will just like we can just like sweeping, and we will count how many edges are crossing our border. So basically, if something crosses the border, for instance, like here, there's the red edge which crosses. So that means that here we do not have the end of the block. Here we are inside of the block. And if we have some, and here we do not have any crossing edges, so we know that we need to end the block. And how to find these numbers fast? Well, we can just count it. So we will do as follows. For each top vertex, which is in the matching, we will add +1. That means that in this vertex I'm starting some edge. And for each edge in the bottom, I will add -1. That means that, okay, here I'm ending this edge. So if I'm going from left to right, every +1 means I'm starting an edge, and every -1 means I'm ending an edge. Okay? And I will just do prefix sums for this. So for every other I have 0. So here I have 0, 0, 0. And I will do prefix sums. That means I will sum these guys. 0 plus 0 means 0. Then I will sum these guys. 0 plus 1 plus 0 is 1. Plus 0 plus 0, 1. Plus 1 plus -1, again 1. Plus 0 plus -1, 0. Plus 0 plus 0, 0. Plus 1 minus 1, still 0. Plus 1, 0, 1. Plus 1, 0, 2. Plus 0 plus 0, 2. Plus 0 minus 0, 1. And plus 0 and minus 0, 0. Okay? I just making the prefix sums, but in the prefix sums I take these two numbers, and then I add these numbers, I add these numbers, and I will just make this sequence. So what can we do about numbers in this sequence and blocks? How they correspond to each other?
Continuous positive numbers are block.
If we have some positive number, that means that we are inside of the block. And if we have 0, that means that we have to end the block. So if we go here, you know that every time we end the block, it's because we have 0. Okay? So we can go from left to right. Okay? And we can just calculate these sums. And every time we reach 0, that means, okay, that we have end of the block. And so we know how to partition into blocks, and now we need to find the minimum inside each of the blocks. So if we can do this like for each block separately, but we can also do one loop for the whole sequence. So basically, in one loop, we can like have two variables, like minimum for A, minimum from B, and like at the beginning of the program, we can just say that these are infinities. Normally, if you want to find the minimum, we just take next vertex and we see whether if it's smaller than actually than the minimum found so far, we just update it. Okay? But now we need to make sure that every time we end the block, we no longer keep these minimums which are in the previous block. So basically, what we can do, we can make this initialization every time we start a new block. Okay? So every time we hit 0 with the sum, we'll just initialize minimum A and minimum B to new values. And previously, we will just but before this initialization, we will say that if these values are not infinity, that means that I have some non-trivial augmenting path, and I will add this augmenting path to some global minimum and global minimum A and global minimum B, because at the end of case 1 and case 2, I need to find globally what is the best path. Okay? So this partitioning into blocks and finding minimum in all the blocks, what is the time complexity of this second phase? It's also linear. Okay? So in total, what will be the time complexity of the whole algorithm? N squared. Because we have n phases, and we have n phases, and each phase will work in O of n. So in total, we have the algorithm is n squared. And this is a really nice improvement. Remember that we started from n to the 5th, we go through n to the 3rd, and now we only have n squared. So unfortunately, this will be not enough for this problem yet, because it can be shown that we can, using some data structure, we can even speed up the linear time of making the phase, and we can make one phase in logarithm time. But this is really when things started to get really serious. So unfortunately, in this today we won't be having a time for doing this, but you can also think about it for yourself, how you could speed it up. But overall, I would like to get some points from today's lecture. So one point is a little bit connected to one question from today's morning discussion, namely what kind of kind of algorithms, what kind of disciplines I need to learn, and I told you that there will be some problems in which you need to mix different things. So, for instance, is this problem what is the discipline of this problem? It's hard to tell, yeah, because from the problem statement, you could say that this is just a problem in which I have two sequences. So it's very easy. The input specification is very easy. But then you can say, I have some dynamic programming approach for this problem, and it's quite natural. So you can say, oh, this problem is dynamic programming. But then you can say, but this problem is really about matching in graphs. So you can say this problem is a graph problem. Although in the problem specification, you don't have any graph. Usually, if you have a standard graph problems, maybe you will have some city with some intersections and roads, and then you know that this is a graph problem. But for this one, it's not very obvious that this is a graph one. And if you want to dive even further into this solution, so in order to speed up the space, you will need a solid knowledge about data structure, which is quite useful, namely segment trees or range trees. So they're named differently. And then you can say that the last part is really a data structure part. So you have this one problem, but you can attack it from very different perspective. And I think it's good to know different perspective for attacking. So this was one thing I would like you to take out from this lecture, even if not taking this concrete algorithm or this concrete problem, but also I would like you to think a little bit about the approach we used for solving this problem. So we started from the very from some solution which was not very fast. It was n to the fifth. Okay, and we didn't say that this is totally useless solution. We took it, and we thought maybe we can speed it up a little bit. Okay, and we speed it up to n to the third. Yes, I know. We thought about a different approach, namely using some graph theory, and we made some work, and we end up with n to the third algorithm, which we had before. So we could think we didn't get any progress, okay? Because we get another algorithm for this problem, but it's not faster than this algorithm we had before. So we could think, well, let's just abandon this idea. It's not very good. But this new idea allowed us to go even further. So we could use the second idea to get even better complexity, and it required some work. But this part from going from this n to the third to n squared, it was I have this algorithm. I see that this algorithm does not use every property of the graph I have in my problem. So I see that my n to the third algorithm is quite general. It solves even harder problems. Okay? But in my problem, this graph is simpler. It has some structure. So I thought, okay, so maybe let's find how this structure allows us to make a simpler algorithm, maybe faster algorithm. And it turned out that we could do a little bit faster here. And this is like this is quite common when you try to solve the problems in the competition. Sometimes like even like the best teams, it's not like they will come up with the model solution just like that. Usually it's a process when you need to find like find some different approaches you can think of about. For this approach, maybe you can find some algorithm which is slow, but then you can try to refine the slow algorithm step by step in order to get something faster. And yeah, and this is usually like the road you need to take in order to solve most of the problems. And yeah, and that's it.